Hello everyone, thank you for coming. My name is Kang from Berkeley Lawrence National Laboratory. Today I'm going to present our paper predicting resource requirement in intermediate polymer transient factory workflow. You may wonder what an intermediate polymer transient factory is. Do not worry, I will explain this term later. This presentation has three major parts. In the first part, I will describe the IPTF workflow and why scientists are interested in predicting its resource requirements. In the second part, I will describe the anomaly detections for outliers in the IPTF workflow data. This step is one of the data preprocessing for the raw IPTF data since anomalies can heavily skew the models we created later. In the third part, I will describe our feature selection methods for building a feed-forward neural network model. Experimental results using different combinations of features are summarized into a Bayesian network in the end. A transient astronomical event, or simply a transient, is an astronomical object or event with a relatively short lifespan instead of having a fixed location in the sky. For example, supernova explosions and gamma-ray explosions are transients. A planet that orbits around a sun is not considered to be a transient. The IPTF workflow aims to search for transients by analyzing images captured by high-resolution telescopes. Analyzing high-resolution images is a time-consuming process, so properly allocating computation resources is important for optimizing the overall throughput of the workflow. This paper focuses on the part of the workflow that locates on NERSC query supercomputer. There are 40 different checkpoints with timestamps of the workflow. The differences between the checkpoint timestamps represents the time spent on a particular application in the workflow. We refer it to the stage processing time. We can roughly divide the applications into three different categories. The first category is called I/O storage, the second category is called computation, and the third category is called database query. To predict resource requirement, we can either predict the time required for processing an image or the number of objects in the image. More computation resources can be allocated to analyzing images containing a larger number of objects and demanding a longer processing time. For processing time, stage 36 is a database-intensive operation for associating candidates within local galaxies. This stage consumes most of the processing time, so we target the prediction on stage 36 execution time. There are a few features available at different checkpoints as shown in the table at the right-hand side. These features are the analysis outcomes of an image at different checkpoints. We can use these features for building our prediction models. Now we have finished discussing the problem definition of predicting IPTF workflow resource requirement. We will discuss data preprocessing that removes anomalous data points from the IPTF dataset. We discovered that the processing time of stages 5, 10, 14, and 19 contains anomalies. These are all I/O stages of the pipeline. Their mean processing time is higher than their 90% quantile. Moreover, their pairwise Pearson correlation coefficients are all greater than 0.9. After further investigation, we noticed that this highly correlated I/O processing time occurs with timestamps that lie in 2015 and early 2016, when query systems was unstable at that time. To remove these anomalies, we remove data points with I/O processing time larger than the mean of the entire dataset. We will justify this method in the next page. The following figures show the pairwise correlation heat maps for all stages. In the figure A, we can observe that the Pearson correlation coefficients are large for the I/O stages. Darker dots mean stronger correlations. However, their Spearman correlation coefficients are not significant in Figure C. The difference of the Pearson and Spearman correlation coefficients is that Pearson coefficient takes the absolute numerical values into account, while Spearman coefficient only considers the ranks of data. Therefore, the high Pearson coefficients are resulted from the large numerical values of a few anomalous points. After we remove the anomalies using the mean value as a threshold, the Pearson coefficients of the I/O stages are no longer significant. These results prove the point that we have successfully removed data points with extremely large I/O processing time. Since the file system issues have been resolved on query since 2016, we discard these anomalous data points and focus on the remaining 90% of the dataset. This figure illustrates the stage processing time distributions after we remove the anomalous data points. It is clear that the stage 36 dominates the overall processing time. Therefore, we still use the stage 36 as our prediction target. To predict either stage 36 processing time or the number of objects extracted, we need to define attributes for making such predictions. There are two constraints for the prediction model to produce useful inferences. Firstly, the input attributes of the prediction model should be available before the output of the prediction occurs. For example, the moment when a model makes a prediction for the processing time of stage 36, the features that are used for this prediction must be available at checkpoint 36. Otherwise, the prediction result is useless for scheduling computation resources, since the program for running stage 36 has already started. Another constraint is that the prediction model should be light-weighted. Since the goal of our research is to schedule computational resources smartly, a heavy machine learning model that consumes a lot of resources is unacceptable. There are three categories of features we can use for predictions. The first category is the historical stage processing time of the current image. The second category contains the attributes at the current image. The third type is the stage processing time and attributes of an image's spatial temporal neighbors. The right-hand side figure labels each of the features. We use a light-weighted neural network with 3 layers for making predictions. In terms of training, we use stochastic gradient descent, which is stable. We illustrate our prediction targets distribution along both spatial and temporal dimensions. It is evident that the processing time at different time intervals and spatial regions are not uniform. Thus, the spatial temporal features should help with the prediction accuracy because spatial temporal neighbors can provide extra information for our models. We evaluate our prediction models using the following settings. We use root mean squared error, normalized mean squared error, and correlation coefficients between the ground truth and our prediction results as evaluation metrics. The baseline of the mean squared error can be set as the following. As a ground truth, images in the same batch of IPTF input stream have exactly the same input attributes available for us to make predictions. The variance of the prediction targets within the same batch is the lower bound of the mean square error we can possibly obtain using any prediction models. The global variance of prediction targets for all data points, on the other hand, is an upper bound of the mean squared error we can obtain. Thus, we can work out the lower bound and upper bounds of the RMSE for predicting both stage 36 processing time and the number of objects. For the stage 36 processing time, the lower bound is 20.4 and the upper bound is 60.4. For the number of objects extracted, the lower bound of the RMSE is 210, and the upper bound is 653. We use 10% of data with the largest timestamps as the evaluation dataset and the rest of data as training dataset. This partition of data matches the case in reality because we can only learn from the past to predict the future. Nevertheless, to further validate our models, we perform a tenfold cross-validation as well. This table shows the accuracy of models trained with a different combination of input features. In general, a larger number of features does not necessarily produce a better model. Introducing irrelevant features can increase the training and prediction time. Moreover, redundant features can also introduce extra noises, which could cause overfitting problems. The best model for both stage 36 processing time and the number of objects extracted are trained with only a subset of input features. Based on the RMSE results, we can observe that rows 8 and 18 are very close to the lower bound of the RMSEs derived earlier. Moreover, the correlation coefficients between the ground truth and the predicted results are more than 90% in general. Based on the results in the previous page, we can summarize the relationships of the input features and prediction targets as the following Bayesian network. The red circles are the prediction targets and the rest of circles are the input features. This Bayesian network is constructed using both domain knowledge and numerical results in the previous table. According to the map, when certain features are used, we can reduce the model size by removing some other features. For example, when the processing time of stage 36 in an image's spatial-temporal neighborhood is presented, other features in the spatial-temporal neighborhood become redundant. Another interesting fact is that prediction of stage processing time depends more on the historical stage processing time. The prediction of the number of objects, on the other hand, depends more on the attributes of the image. In summary, the IPTF workflow demands supercomputing resources for high-resolution image analysis. Predicting the stage processing time and the number of objects in an image allows better computational resource allocation. In our approach, we remove the I/O anomalies at the data preprocessing stage. Then we build models for prediction targets using a different combination of features. Finally, we use the results of the model to build a Bayesian network that summarizes relationships of input features and prediction targets. Thank you for listening. If you have any further questions, you can check our papers or you can directly contact us.